So in chapter 8, we're up to this current in history version of what do I do if I can't solve the integral, which is what's going to happen in real life, right? Um, so it's a Diffie-Q, basically, right? So what do I do if I can't solve this Diffie-Q? Well, at the level we're at right now, we're about to show that I can write a function like e to the x as a series. So so it turns out that e to the x is a Taylor series. Not that you need to know what that is yet, but I've got a nice little list of some famous Taylor series here. Give me 1 second. There it is. E to the x is the sum of n equals 0 to infinity of x to the n over n factorial. Yeah. So meaning, and this is one of the things that you're going to have to do is, especially if this feels like completely foreign to you, is you're going to have to write out term by term to really understand what's going on here. So I do that first kind of really a dumb version of it, okay? So that is x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial. So I'm not simplifying anything as I do this, right? You hear me? And so it turns out x to the 0, it used to not be 1. We said be careful if it's 0. 0 to the 0 is trouble sometimes, but now we're going to allow it to be 1. So this is 1. 0 factorial is 1. And then 1 factorial is 1. And so then you can see the pattern pretty quickly of what's going on. Can you tell what 3 factorial is? Do you know it? Does anybody not know what a factorial is? So 3 factorial is 3 times 2 times 1. So that's how I got a 6 here, right? Zero factorial is always 1. If you want explanation on that, I'm happy to talk about it. It's a probability thing. When I say factorial, I'm saying how many ways can I arrange 0 objects? Well, I don't have anything to arrange, so only one way, by doing nothing. And then 1 factorial, how many ways can I arrange 1 object? Right? You know what I'm talking about? Like I've got a mouse, a book, a pad. How many ways can I put them in a row, 3 in a row, right? So that's what it's saying. If I have 3 objects, how many ways can I arrange them? It's 6, right? Imagine the objects are 1, 2, and 3, right? So I could do 1, 2, 3. I could do 1, 3, 2. So I started with 1 both times. Now I can start with 2, 2, 1, 3, 2, 3, 1. Now I started with 1 every way I could do it. I started with 2 every way I could do it. I could start with 3, 3, 1, 2, or 3, 2, 1, and there's no more choices. So there's my 3 factorial is 6. But this is not the calculus piece of it. This is a probability piece, or counting. So if you ever anybody take stats, statistics, even in high school? In high school maybe? Yeah. And so do you remember doing probabilities in there? Right? So it's really related to probabilities. But look at this now. Look at what I have. The integral of something that I cannot solve is now something I can solve quite easily, right? So now all of a sudden I could take a function and turn it into a sum of polynomials. And of course, to integrate those is very, very simple. And I'll show you something like at the end of the chapter 8 that if I did this particular, if I did this integral with Simpson's rule and 4 partitions, I'd get a better answer with 4 terms from a Taylor series. So again, we're just trying to improve on things, right? I mean, this is probably 100 years old now, but we haven't improved on it. We don't need to. It's so good. No one's a grad student in mathematics trying to come up with a better way to estimate an integral anymore. They're working on other problems, right?
So that series is for e to x?
Yeah.
And then our original integral is e to x squared?
Yes. Good point. Sorry. So e to the x squared just gets, for x, it gets a replacement with an x squared. So it's really that simple. I still get the same first term, but my second term is now x squared, right? And then I get an x to the 4th, and then an x to the 6th, etc. So you'll see I'll have even terms of the original series or odd terms of the original series, yeah. But you get the idea, right? So, but coming up with the actual the series, and whenever I say series, I'm talking about a sum. Okay, coming up with the actual series is the real depth of what we're doing. But after I get that original series, it's easy to make any other function. Okay? So that's the idea. The idea is, now remember, all right, I've got this integral, but what do I want to make sure it does? So now I've got an easier integral to deal with, right? But what do I want to make sure it does? I want to make sure it converges, right? So I have to do all these tests. I want to make sure, if I spend all this time coming up with a replacement series and it doesn't converge, why bother? Right? So that's the same idea. You're out there in the field, you think you've got this solution, right, of the problem you're trying to do, but you can't do the integral because it diverges, then you don't have the solution. You got to think of something else. So that's chapter 8. 8.1 and 8.2 should be a review. I'm going to try and go through those today, but you've got to control me. If I'm going too fast or doing things that you don't understand, like factorial, it could be something that simple in the middle of my lecture that throws you off for hours. So you got to ask. You got to make sure you ask. Well, what is that funny looking, right? What is that funny looking symbol there? Well, that's actually sigma. It's a capital Greek letter S, and you've already seen it from Riemann sums, right? Right? What do we have? The sum of I equals 1 to n of f of x sub I times delta x. And if I throw the limit on there, it becomes the integral. And so you see the Greek letter S becomes my letter S, right? For the integral sum. Okay, so we start with 8.1, and we're talking about sequences. So a sequence is just a series of, sorry, not a series, it's just, it's a set of numbers, right? And we're trying to figure out the first term, we're trying to figure out the last term, something like that. So typically I use nth term notation. So 8.1, we're talking about sequences. And so like a pretty famous sequence is 1, 1, 2, 3, 5, 8. Do you see what's coming next? Anybody else? Fibonacci. Anybody see the next number? 13. So I'm taking the previous two numbers and adding them to get the next number. So I'd like to be able to write out a sequence. And if I can, I'd like to generalize it. So for example, so this guy's called the Fibonacci sequence. I could be talking about an nth term. That's the notation I prefer. So something like this. So part of the problem is, if I give you an nth term, can you write out the terms? Obviously, yes. If I give you the terms, can you tell me the nth term? That's the trickier one. But on this one, right, and the book uses a weird notation here, but I just write it like this. When n is 1, what do I get? So again, I'm going to, you know what I'm saying? When I'm doing these, especially if I'm a newbie, I'm going to do my initial write out as dumb as I can, meaning as baby step as I can, meaning don't simplify anything, right? And then I'll rewrite it, right? So what do I have? 1 over 2, comma 2 over 3, comma 3 over 4, right? So where's it going to? Can you tell where it's going to? What number is it getting closer to? 1, right? 4 over 5. A billion over a billion and 1 is really, really close to 1. And it's kind of nice to put these to plot them, to see if it kind of says, hey, is it going somewhere we recognize, or is it not going somewhere, right? So I like to do this. Brand new web page, right? So plot sequences on Desmos. And so you see I'm going to define my nth term like a function. Do you see it here? And then plot I don't have to do that. I think I can just do a of n equals n over n plus 1. So let me just do that. So a of n equals n divided by n plus 1. All right, that's giving me my whole function. That's not quite what I want. I just want to see the points. I just want to go to Desmos. Oh, here it is. Oh, it can't do the n. Let me try it this way. Put it in as x's. Nope, still giving me. Somebody do a quick research for me and find out how I plot this. I just want to see the notation, and once I have the notation, it's simple. Maybe that's it. Try again. So I want a subscript. Shift minus. Thank you.
I found that out the hard way.
Still not giving me the points. I only want the points, right? The single values. What'd you find?
Find one. Find a list.
What'd you do? Yeah. Oh, okay.
Yeah, capital N is like using N in the lowercase n.
Gotcha. In the list of numbers, yeah. All right, I'll try it. I want to go back to my function notation then. And then use capital N. Damn it. What? We're building
When the
furniture?
details take precedence, the
Skip
rest
ad.
falls perfectly into place.
Hey, welcome back to Calculus. In this short video, I'm going to show you how you can use Desmos to graph sequences so you can visualize our work as we're working in the Chapter 11 stuff. I tried to do this in the first part of the 11.1 video, but I guess the screen I thought I would. And then maybe I'll just use one of our first examples.
I got it.
All right. So then Desmos is asking me if I want.
Damn it. I've done it before, I just can't remember anything. So I'm just going to plot a single point, n, comma.
I figured out how to plot the, like a list.
Oh, yeah? Ah. Oh, I want this as n plus 1. All right, well,
You take the original function.
Yep.
And like lowercase n, and you make the list with capital N equals, and then just square brackets,
nice.
and make a list, and then take the point of capital N and a of capital N.
Okay.
To make n a slider.
It seems a
Is the
little bit.
maximum n and how much to step by
Oh,
1.
this
And you can
is
see it
another
drew a
one.
little dot. So I zoomed out there on accident. It drew a little dot. Now as I move the slider, I'm changing the value of n, and well, you can see the sequence. Here n just got to 10, 1 over 10 is the value, and got to 15, and so on. So I think that's a pretty effective demonstration that this sequence is going to 0. Yeah.
Anyway, work on it. Make sure you get yourself a nice version of a sequence here. So, so there's a lot of this writing out and then trying to come up with a version of it, right? So let's just do one of those because that's the first type of question we have. So find a formula for the nth term, right? So I'm looking at number 5 here. So what do I have? 1, 1/3, 1/5, 1/7, 1/9, right? So I've got 1, 1/3, 1/5, 1/7, etc. I want to find a sub n, right? Well, first of all, I could see that that first term is really 1/1, right? And this is, I'm trying to just to play kind of crime scene math version, right? You're a crime scene investigator. You're trying to figure out what the hell created this pattern. So I can see that I need odds. I need a sequence for odds, right? So notice what happens if I just start writing out the odds. The first odd is 1, the second odd is 3, the third odd is 5, etc., right? And from here, I can see my y values are increasing by 2 every time. So it's telling me a slope of 2, right? You with me? So m is 3 minus 1 over 2 minus 1. Sorry, what did I do? 3 minus 1, yeah, over 2 minus 1, which is 2 over 1, which is 2. I figured out my slope. All I have to do is figure out the b value. And I don't know how long it's been since you've been in Algebra 1, but if I can add 2, I certainly can subtract 2. So if I go 1 less, I'm going down to minus 1, and that's my b value. So my a sub n is actually 2n minus 1. Yes, yeah. So remember, I'm just doing my odds. This is my nth term for odds, because I'll use this quite a bit. And now, but for us, our problem is a sub n is 1 over that 2n minus 1. Yeah. So once we come up with a pattern, a general term for odds, we want to memorize it. If we're not going to memorize it, it's going to go on our formula sheet. Okay? Yeah. Yeah. So I figured out that my pattern for odds, right? That's what I'm working on in this box, yes? So the first odd is 1. The second odd is 3. The third odd is 5. And I realize that that's linear. How do I know it's linear? X's are changing by the same thing. Y's are changing by the same thing every time. Not the same as each other, right? But I know I'm going upstairs, right? So I figure out that pattern just using a y equals mx plus b. And then keep it. Store it, right? Let's look at another one. I'll wait for you, Daniel. You okay, Daniel? You need a photo of that? You okay? Look at 10. 10 is kind of interesting. 5, 1, 5, 1, 5, 1, 5, 1, right? And this is a kind of fun one to come up with. Well, it looks like I started with a 5, and then I subtracted 4, and then I added 4, and then I subtracted 4, and then I added 4, right? So I could come up with something here for an nth term, possibly by turning just a sign on or off, right? A plus on or off, right? You with me? So I want some kind of plus or minus 4 here. And I want that plus or minus to turn on and off as I go, right? So we'll probably just think of the on or off, right? How could I just come up with an on or off? Yeah, yeah. So I want to be thinking of -1, +1 kind of thing, right? I don't know if it's the way I'm going to go, but I can do this simply by saying -1 to the nth power, right? -1 to the nth power. When n is even, it's going to be a positive. When n is odd, it'll be a -1, right? So there's one I want to think of, right? A sub n is going to be what? +1, -1, etc., right? So what do you think? How are we going to come up with this A sub n? This one doesn't work, of course. What do you think? These are fun. This is fun to me. It's like a little problem, pattern matching thing that we're all pretty good at as humans, right? What do you think? You got an idea? Say again. Yeah, but try it. Write it down and try it. So what did you say to try? A sub n is what? I'm sorry, I can't. A to the n? Right, but remember what I want. I want a 5 and then a 1 and then a 5 and then a 1 and then a 5. I want it to keep changing from 5 to 1, right? So the first term should be 5, the second term should be 1, the third term should be 5, right? The next term should be 1. Anybody gonna give us a shot here? What is it? 3? Okay, so nice. So 3 plus my -1 to the n times 2. Looks like it might work. So when n is 0, right, that -1 is a positive 1.
Yeah.
Right, so that's 3 plus 2.
But I think that doesn't start at 5.
Yes. So
1 is 5.
yeah. Oh yeah. So I actually was starting at 0, and that's something I can do anytime I want. So if I want to start at 0, I can. A little bit tricky, but so I would say something like 4n equals 0, 1, 2, etc. Or I could start it at 1, like you're saying, and I like that, and then I just want to shift my n by 1, right? So what if I do 3 plus the -1 to the n plus 1 times 2? Yeah, so probably yeah, I'm always trying to make it as simple as I can. Let me try yours now. 3 minus a -1 to the n times 2, right? So now when n is 1, I get a double negative, I get the 5. There it is, right? Yeah, I like that, Alex. When n is 2, that -1 becomes a positive 1, but it becomes 3 minus 2, and that's 1. So that's it. That's pretty good. So our first problem is write out terms or find me the nth term. And they get tricky. okay? Sometimes you just have to look at the pattern. Sometimes there's no choice. Like number 8. Well, look at the top. -1, then +2, then -3, then +4, right? So we know how to generate the top already, but look at what's happening downstairs. 4, that's 2 squared. Then 9, that's 3 squared. Then 16, that's 4 squared, right? So I sometimes I'm just going to have to be able to look at it and figure it out, right? Yeah, so I please figure out the Desmos version of it. Be able to. You got it? Can you just send it to me? You got one that's you built?
Yeah, I found something online.
Oh, let me see.
So you have to put in like n values first,
Oh,
and then you put in the function. Then you
and then you do that. That's what Alex was telling me.
yeah.
Send. Will you? Can you send it to me? Save it and send it to me. Because I don't want to type it. I'm lazy. Sorry to make you do that. Got it. I like it when someone else does the work for me. So
I also linked the video.
oh, okay, nice. So it looks like I just right. So this is my process. Did you actually save the file and send me the file?
Oh,
No, that's fine. You just gave me a screenshot. It's fine. I'll type it. Yeah. Um, so showing what Noah just sent me. I'm gonna write, and we should all do this, right? Write out the natural numbers, listed natural numbers, come up with the a sub n notation of the nth term, and then the key is going to be that last one. I haven't had that much of a difficult time before to write these out, but 1, 2, 3, 4, 5. Let's just do 5 terms for now because I'm lazy. Oops. Yeah. And it will just keep going.
And then the final.
Oh, okay. Nice. Comma. 10. Nice. Hey, I'm learning lots. An nth term, right? So a of n, and I'm going to do the one we just came up with the 5 and the 1, right? It was 3 minus the negative 1 raised to the n times 2. I might put the 2 out here, prettier. And now, finally, right, this notation, which is going to be plotting the 2 points, right? Sorry, the coordinates. And there it is. Huh. Thank you. Thank you, Alex and Noah. Go ahead.
Convert that to a table.
Oh, be nice. Where is that? In the wrench?
No, the gear.
Oh, the gear. Where's my gear? There it is. Oh, there it is. Table, right? Beautiful. No. Control Z. Control Z. There it is. Nice. So, pretty simple, right? But it's going to be a good tool. Why? Because we want to start talking about when does a sequence, right, a list of numbers, when does it converge or not? It's the same as a limit, right? You really can think of this as a limit. Does this one go somewhere? No, this is an oscillator, right? So we want to think about Calc 1 in the same respect of when did we fail to have a limit? Well, when it was unbounded and just went up forever, right? When it oscillated, right? What's the other one? It kind of broke. I don't think we're going to get that. Thank you, Noah. So going back to our book here, we say our first definition, a sequence has a limit L, right? So you can see it's just a limit. If it does have a limit, it converges. If it doesn't, it diverges, right? So that's the next thing in our list. When we're looking at 8-1 problems, we're going to say, does it converge or not, right? So it's pretty easy to tell from the points. It's also easy to tell from the function, right? I really can take a limit as n goes to infinity. Look at number 23, right? So I've got n squared e to the minus n, right? So n squared e to the minus n. Right? Not much different than me looking at the actual function and deciding if this is going to converge or not, right? But that's our main thing. We say a sequence converges, right? A sub n converges if the limit as n goes to infinity of a sub n is L, and that's some real number, right? I need that thing to be a real number. So it can't be plus infinity or minus infinity, right? And it can't oscillate. It's got to get somewhere. So it's as simple as treating the sequence or the nth term as a function itself, right? So I'm saying, does a sub n equal n squared e to the minus n converge? Well, if the limit as x goes to infinity of a sub of x squared, right? X squared e to the minus x so this is already something called the limit comparison test, right? So all I'm going to do is turn my sequence into a function and see if that converges, right? See if that heads to some number. How do I do this limit? Say it again? L'Hopital's, nice. So you're going to see all of that little L'Hopital stuff is going to come into play. As x goes to infinity, what happens to x squared? Goes to infinity. What happens to e to the minus x? Goes to 0. I need to move one of them, right? Upstairs or downstairs so that I can do this L'Hopital piece. So this is the limit as x goes to infinity of x squared over e to the x. How do I know to move e to the x? It's already got that reciprocal piece built into it. And remember, I'm going to be taking a derivative, right? So if I move the 1 over x, if I move the x squared downstairs, think about what's going to happen to that derivative, right? It's going nowhere. I mean, it's going somewhere, but I want it to go nowhere. So now I'm going to take a little hop here, right? I've got the limit of, as x goes to infinity, of 2x over e to the x. Right? Do you see what happened there? I took a derivative of x squared. I took a derivative of e to the x. I redo my limit. Well, where is 2x going to? Infinity. Where's e to the x going to? Infinity. So I got to hop again. Right? So I get 2 over e to the x, and finally this guy's going to 0, right? Pretty simple, yes? Well, think about what's happening to this particular piece, right? You can kind of see the terms, yes? You can see the points going to 0. It looks a little different than that, but you get the idea. So, one of the things I can figure out if a sequence is converging or not, is if it's always decreasing, that's a good sign, right? But it has to decrease and level out. So I need it to be decreasing and bound below, or increasing and bound above, right? That's my next theorem. Sorry, trying to find it. Here we go. A sequence always increasing or always decreasing is called monotonic. Okay? So if I can simply prove that a sequence is monotonic and bound above or below, I've got it being convergent. So there's a simpler version of finding a limit, which we know how to do, so there's not going to be many of these that we can't figure out. But oftentimes it'll be easier just to be able to show that it's always increasing and there's a higher point. There's a highest point, right? So every bounded monotonic sequence is convergent. That's what we want. Now, it's easy to tell if something is increasing or decreasing, and we did it in Calc 1. Do you remember first derivative test? So we're going to do first derivative test to show that we've got something monotonic, right? If f of x has, sorry, I want to find a derivative. It's the easiest way, right? If f prime of x is negative, right? Then f is decreasing. Just the first derivative test, right? If f double prime of x is always greater than 0, then f is increasing. And then we just have to find a bound, but that's pretty damn easy. Right? Think about it. If we found a bound above, yes, or a bound below, we're talking about a local min or local mins or maxes kind of thing. Let's see what the book says. So like number 55, show that the sequence, right, the sequence that I have. Oh, I don't want to do this one. Yeah, here we go. 49. Does it converge is the question. Well, pretty simple, isn't it? I don't even have to use this monotonic piece. And I said that. Often we can just take the limit and know. But you'll see things are going to get a little bit crazy, so we'd like a different version of this. And so 49, I've got a sub n, sorry, a sub n is 1 over 2n plus 3. I already know the limit as n goes to infinity of 1 over 2n plus 3 is 0. So I already know it's convergent, right? But I'm saying I want to show that it now also has this property of being monotonic and bounded below, right? So what we do is we convert into a function. We find our derivative. So I get negative 2 over 2x plus 3 quantity squared. And notice that that is always less than 0. Right? Always less than 0. We got to be thinking of our domain, though, certainly, because I would be in trouble if x was what? Negative 3 halves, right? But remember, we're talking about the integers. We're talking about our 1, 2, 3, 4, so I'm not worried about that piece. What's the very next term? So if a sub n is 1 over 2n plus 3, what is a sub n plus 1? Right, I'm just going to put an n plus 1 in there. So I already know it's decreasing, right? How do I figure out what the lower bound is? Say again? Yeah, well, once I take the limit, I already know it, right?
I guess
Yeah. But it's pretty, um, I don't know why I did this, but um, it's pretty easy to tell, right? That this thing is never going to be negative. So a lot of times my bound is just coming from an observation, right? I can really tell that this thing will never be negative. So I know 1 over 2n plus 3 is always greater than 0, which gives me what? 1 is greater than 0, which is true. So I know it's bounded below. It's really trust your gut kind of on it. So it's asking you, right, on a bunch of these, is it bounded? And then how can you find it? Of course, the ultimate bound is the limit, right? Alex said that. If you can find the limit, you know the bound. It's not going to go past that. We can have limits that are we can have limits, right? Like x sine x, right? Or sine x all over x, that type of thing. Right, sine x over x, right? That thing is looking like a sine curve, but it's getting smaller and smaller. And in that case, I wouldn't have a lower bound at 0, right? So that's where we have to be careful. That particular limit is not my lowest bound, but certainly -1 would be the lowest bound for that particular one, right? Say again? Yeah, exactly, but it's a lower bound. That's all I need. But here's the issue with this one, of course, it's not monotonic, right? So this is one we would not use that monotonic, would not need to. We already know what this limit does. All right, so in 8.1, I mean, I certainly like problems up to 51. Yeah. Yeah. Up to 50, up to 51 is pretty good for 8.1. Okay. And again, when you're doing them, write them out like in baby steps, right? All right. Let's take a little break. Let's come back at 10.